Okay, my intention is to make this a quick video about sensitivity, specificity, positive predictive values, and negative predictive values. So this is what we're going to be working from. I got this from the website that I posted in Blackboard. Here we have the truth, and here we have test results. So we have presence of a disease, absence of the disease in reality, and then we have the test says positive or the test says negative. And then we have true positives, true negatives, false positives. Total of the test positives, total of the test negatives, total of those diseased, total of those not diseased, and then the grand total. Alright, so prevalence is the proportion of individuals in a population having a disease or characteristic. To estimate prevalence, researchers randomly select a sample from the population that they want to describe. For a representative sample, the prevalence is the number of people in the sample with a characteristic of interest divided by the total. So we have the total number of people in the sample with a characteristic over the total number of people in the entire sample. So that would be A plus C, which is the total of disease, divided by A plus B plus C plus D times 100. So how is prevalence different from incidence? Incidence is a measure of the number of new cases of a characteristic that develop in a population in a specified time period, whereas prevalence is the proportion of a population who have a specific characteristic in a given time period, regardless of when they first developed the characteristic. We don't use this contingency table for incidence. The incidence is the total number of new cases in some time period over the population at the start of that time period. So sensitivity is the probability that a test will indicate disease among those who actually have the disease. So sensitivity is this cell here, A over A plus C times 100. So it's the true positives over the false negative, the true positives over the true positives plus the false negatives. So you could just do A over the total times 100. Specificity is this cell right here. It's the fraction of those without the disease who will also have a negative test result. So it's D over B plus D, or just D over the total, times 100. But sensitivity and specificity are characteristics of the test. The population does not affect the results. Clinicians and patients have a different question. They want to know about truth, right? We want to know if we have the disease or not. So what is the chance that a person with a positive test truly has the disease? If the subject is in the first row in the table, what is the probability of being in cell A to being in cell B? A clinician calculates positive predictive value by looking at A over A plus B times 100. So similarly, what are the chances that the subject with the negative test really doesn't have the disease? This is in this corner, the negative predictive value. So the negative predictive value is D over D plus C. We're looking at the row, times 100. So let's look at an example. 100 people are tested for a disease. 15 people have it, 85 don't, so the prevalence is 15%. So 15 have it, 85 don't, so 15 plus 85 is 100, so over the total we get 15%. So what's the sensitivity? Here we are. We're looking at this cell. We have 10 over 10 plus 5, or 10 over 15, which is 67%. So the test misses 33% of the people who have the disease. So what is specificity? Specificity is this cell here. We have 45 over 45 plus 40, which is 85. Okay, so we have 45 divided by 85 times 100, and we get 53%. In other words, 45 people of 85 with negative results are truly negative, and 40 test positive for a disease that they don't have. So these guys are truly negative, and these guys test positive, but they don't have it. But we really care about positive predictive values and negative predictive values. So what's the positive predictive value here? We figure that out by doing A over A plus B, which here is 10 over 10 plus 40. We could just say 10 over 50, and we get 20%. So only 20% of the people who test positive actually have the disease. Is that good? Not to me. Let's look at the negative predictive value. That's this down here. We want to do D over D plus C. So 45 divided by 50, 90%. So for those that test negative, 90% do not have the disease. That's not bad, but we want both of these values to be very high. Let's look at another example. Same test, but we increase the prevalence. All right, so the prevalence now has gone from 15%, we doubled it to 30%. Because sensitivity and specificity are characteristics of the test, they're the same. All right, so we still have 67% sensitivity and 53% specificity. We want these to be much higher for a better test, but sadly, that's not what we have. So we care about the PPV and the NPV, so the positive predictive value is A over the total, so 20 over 53 divided by, multiplied by 10 is 38%. So now 38% of the people who test positive actually have the disease. When the prevalence increases, our PPV increases, which makes sense, right? Now what do you think happens to the negative predictive value? When the prevalence increases, that decreases. So let's look, we have 37 divided by 47, and we get 79%, so it decreases. So using the same test in a population with higher prevalence increases positive predictive values. Conversely, increased prevalence results in a decrease in negative predictive values. When considering the predictive values of a diagnostic or screening test, recognize the influence of the prevalence of the disease. The figure depicts the relationship between the disease prevalence and the predictive value in a test with 95% sensitivity and 95% specificity. When considering the predictive value of the diagnostic screening test, recognize the influence of the prevalence of the disease.